So today's webinar number 1 for the Introductory Youth Astronet Professional Development Seminar kicks off a 3-week period during which you guys will learn to use the telescopes, the image processing tools, examine the different curriculum resources that we have, the online environment for teaching and learning and for working with students. Each webinar will be between 60 and 90 minutes. There's webinar number 1 is offered today and tomorrow. Webinar number 2 is offered Wednesday and Thursday next week, and webinar number 3 the following week. That last webinar is kind of a live wrap-up. It is optional, but strongly encouraged. But additionally, Erica will be offering and scheduling live office hours on the dates you see there, the 13th, 15th, and 20th. And basically, she'll just be online all day, and you can click onto this link if you want a personal tutorial or there's something you haven't figured out. So your job this week is to be learners yourselves, as opposed to we'll worry about how to engage students with these resources in the later weeks. So the thing we really want to do today is introduce you to the centerpiece of the Youth Astronet program, which is our MicroObservatory telescope network. And once again, the image on the left shows 2 of our scopes in Arizona at the Whipple Observatory. And on the right is a picture of the telescope on the roof here with some local students who learned to use the telescopes and got to come for an in-person visit. But remember that as you offer programs, since you're all over the country, you have an opportunity to request a virtual visit with Frank in the telescope lab or with scientists here at the observatory as well. So the telescopes, you can see they're about 3 feet high. They are robotic. There's no human between your human in the loop between your sending them requests for images and them returning the requests to your account the next day. Although Frank, pictured here, does keep the telescopes working. I'm going to show you how to take an image in a moment, and each of these features of the telescope, you'll see how you end up interacting with the physical instrument. So the telescopes are reflecting telescopes, meaning they use mirrors rather than lenses. And they have a 6-inch aperture or opening. And since a lot of students, actually youth and adults alike, have the misconception that the main thing telescopes do is magnify. In fact, the main thing they do is gather light. And so that's why astronomers like really big telescopes. The bigger the opening, the more light the telescope can gather. Ours are 6-inch, so they aren't terribly big, but the one thing they do allow is for longer exposures. So you can request exposure times from a fraction of a second to 60 seconds. The telescope also has a filter wheel that's in pink here. You have an option to set whether all the light hits the detector, the digital detector, or to separate out red, green, or blue light. The detector itself is not very high resolution by iPhone standards. It's only 650 by 500 pixels. That's about a 1 megapixel resolution. But the thing that it does allow is it's sensitive to very dim light. And in fact, It gives allows up to 4,096 brightness values, and you'll see how that comes into play a little later during this webinar. I just am giving you all this information about the telescope because you'll see these features of it come up as we learn how to use it. So you're going to access the telescope through your YouthAstroNet account. The MicroObservatory telescopes do have a public interface, which is at microobservatory.org, but all the features that you get with YouthAstroNet and a special interface that keeps your images for you right in your account is the one you want to use. So that link to the YouthAstroNet website is on the slide. I'm sure Erica has sent it to you. It's also, if you go to microobservatory.org, there's a little link right at the bottom to YouthAstroNet. And so let's go there now and learn how to take an image. So again, remember that there, right now, Erica created accounts for you in 2 portals within the Educator Portal, which is where you're going to participate during this online workshop. It looks like somebody has already introduced themselves. One thing you'll notice when you're on the portal is that if there are new posts to any of the discussion forums, your account will keep track of that and let you know how many if there's any you haven't opened yet or read. So the Educator Portal is where your checklist for this workshop is, but it's the activity portal where your youth will work, where your students will work, and also where the access to the telescopes is. So I'm clicking on that right now, the YouthAstroNet activity portal. And a few things just to note about the interface. This environment is built on an open source learning environment called Moodle, but it allows a few things. One is it is accessible with mobile devices as well as on desktop computers. You can maximize your screen by, you'll see I have a navigation panel on the left here. Do you see that?
Yes.
Okay, so I'm no longer surrounded by green here. Anyway, but I could get rid of that and sort of make more room just by clicking a little toggle switch here in the menu bar. So the items marked with a little chat box are discussion forums. We have a glossary of scientists and experts with different career profiles to explore. But the key thing we're going to use today is our robotic tools, MicroObservatory robotic tools. So I'm going to click on that to open it up, and you'll see there's 3 functions in the robotic tools. One is to request images. Secondly is to get the images that you requested before. And thirdly is to actually work with the images in an image processing environment called JS9. JS stands for JavaScript. So let's first request an image. And I'm going to ask for a little participation here in terms of whoever finds the chat box first to identify a target they want to take a look at. We'll choose that target. So this is
Andromeda response.
oh, Andromeda. Okay, Chris, you get the prize. We'll go take a look at the Andromeda galaxy. One thing you note about the way the targets are organized is that they're organized the same way the universe is organized. Objects in the solar system, objects outside of the solar system but in our galaxy, stars and nebula, and then galaxies outside the Milky Way. This is a key learning point for students. Often, you know, we cover astronomy in grade school. Students learn about the planets, and they often don't distinguish between solar system, galaxy, and universe. Think of them as all the same thing. So we try to reinforce the address, the hierarchy of the universe through our interface. Okay, let's take a look at Andromeda. And again, you'll see that you get to set several settings for this target. One is the field of view, and that is identifying, if I go back to, actually, if I go back to this slide, in addition to the main camera here, which has a field of view of 1 degree, there's a finder camera, this little 1.5 inch opening at the front of the telescope. And that gets a wide field view of the sky, more like 10 degrees. In fact, if I show you, the normal view is if you held your pinky up at arm's length, the image that comes back from the telescope would be about the size of your pinky fingernail held at arm's length. That part of the sky would be covered with your image. For some objects, like Andromeda, you can choose a zoom view, which actually just changes the optics on the telescope, so less of the object, the object is zoomed up on the detector, and that wide field uses that finder camera, and that's about a 10-degree field of view. So by 10 degrees, I'm really talking about the angle. If you had a string from my eye to the bottom of my fist and a string to the top of my fist, that angle would be about 10 degrees. So there'd be 9 fists, 90 degrees from the horizon to the top. So astronomers work a lot in angles. So let's go back to our Andromeda telescope interface. I'm going to choose the normal view, is typically the one you most want to use. You have several exposure time settings, and this is really setting how long the shutter is open inside the telescope. For dim objects, you want well, actually, let's have a prediction here. Any predictions as to whether we want a short exposure time or a long exposure time for the Andromeda galaxy? And in your chat box, say why you think it might be short or long. Giving a little wait time here. Okay. Oh yeah, I should mention, you can, if you don't want to publicly take a risk and guess, you can make a private message to me. So we have a few different theories. Longer exposure, dimmer equals less light, so longer means more light can enter. We have shorter because the Andromeda galaxy is actually close to us. And a long exposure since it's a distant object. So again, now this closeness and distance is a little relative with the Andromeda galaxy. And it, almost all galaxies are very dim. So typically you do want longer exposure times. I will say, for those of you who had a little information about Andromeda in particular, I'm going to click on 45. Image may be underexposed. If I click on 60, we give a hint on the exposure time. So a 60-second exposure is typically what you want for almost all galaxies. The Andromeda galaxy, you probably would get an image at 45 seconds because if you're in really dark skies, it's actually a naked eye object. You can just see it with your naked eye. Although I want to mention at this point that we do not, for most targets, we don't actually allow the non-optimal exposure times. We're working on offering that for some objects, but of course the reason is if for every object we took 3 non-optimal exposure times and 1 optimal, we'd be spending 75% of our telescope time taking bad images. So anyway, Andromeda is a longer exposure time. It's a dim object. You want to let more light in. And you now have a filter selection, and that is controlling a wheel of little pieces of glass that go over the CCD detector. And either the glass is clear, so all the light is let through, or it's colored red, only letting red light through, blue, or only green. I'm going to take multiple. You could do this one at a time, but if you click this multiple filters, the telescope will send you back 3 separate images at once, and it just keeps you from having to go through this interface 3 times. So it's a nice shortcut. So I'll hit continue, and now we've taken that image. Now notice it says right here, Andromeda Galaxy was requested for MDUSALT. Click here, and if I click there, I get to that second area of the robotic tools. This is my image list, and you see that my 3 requests that I just made for red, green, and blue Andromeda Galaxy images at 60 seconds are in there as pending. Now, I also asked for a sun image earlier today, so that's pending. And these dark images we'll talk about in webinar number 2 when we talk about some advanced image processing. But essentially, anytime you request an image, the telescope is also going to send you, the system is going to send you a few images taken with the shutter closed, basically with a dark opaque filter over the detector. And we'll talk about that next week, but they are used as calibration images. So this is a real instrument, and we'll talk about that later. So I just, question. Good question. What telescope is going to be taking these images? The way our system works is that telescopes in both locations, both here in Cambridge and in Arizona, and should we be so lucky to get a telescope in another location this year, we're hoping to, possibly later this year. Anyway, telescopes in all the locations will take the image, and there's there's software in the background that looks at the resulting images and looks at the dynamic range of the images and puts the best image in your archive, in your list. So the Andromeda is going to be taken in Cambridge and in Arizona. And tomorrow I'll be able to find out which telescope actually took it, because I'll have the image, and the image comes with information about which telescope took it. But through this interface, you don't specify. Okay. So we've taken an image. Are there any questions, up to other questions about how the telescope itself works? All right, so your mission, right, over the next week is to request lots of images. And now I'm going to show you what to do with an image once you have it. And you'll see that I requested a lot of images day before yesterday, and they all came in. I requested some images last week, and then just a few images today. Okay, so your images are listed in your personal archive by date, with the most recent ones at the top. I should mention that we only keep images on our servers, and these are connected to our servers, for a month after you take them. So if you or your students end up collecting images that you really like, you want to save and download them to your own hard drive, which you can do, and you'll see how to do that later. Otherwise, because they'll disappear from your archive after a month. Okay. Where's the wait time? Yes, so, right. Images are taken night to night. You request them one day, they're taken that night, you get them the next day. How many images are taken per night on average? Well, typically the telescopes, since they're 60-second images, and it kind of depends on how much dark time there is when the sun sets and rises. But typically we schedule images so that each telescope might take 100 images over the night. So they're, and they can take as many as 200 images per telescope over the night, so several hundred. Oh, we have lots of questions. This is great. Okay. Can you request an image in advance? For example, the moons of Jupiter for the next 7 nights. You have to log in each day. Yeah, you have to log in each day and collect that. Although I want to note that on the moons of Jupiter, if we go back, which, by the way, isn't up at this time of year, so you note that Jupiter is grayed out. But, you know, in a few months, when it's back up, if you ask for Jupiter's moons, you'll actually get 5 images taken an hour apart from that night. And so you can actually see in one night the motion of the moons. That's what this observation does. The place we're hoping to put a microobservatory telescope is actually in Chile. We're at our southern hemisphere location, but there's a lot of both diplomatic and technical issues to be worked out in putting a telescope there. So, but Frank is, that's definitely on his list for this year. Great questions. All right. Now let's take a look at what to do with those images once you have them in your archive. So I'm going to go back to the main page. And I'm going to open my tools. We've already seen my list. Now we're going to use the images in the JS9 image processing tool. There's 2 ways to actually open an image in JS9, and I'm going to show you both of those ways. If I go to my image archive, I can just click on an image. Here's the moon from last night. I click on it, it just opens a new window with that image in it. Now, you'll note that there's nothing in this. This image is very gray looking. And in fact, this is one of the features of the telescopes you might have noticed in those pictures in Arizona. They sit out in the open and they take images no matter what the weather. And it was cloudy in both Arizona and Cambridge last night. So in fact, what I have is a cloudy image. But I just wanted to show you one way to open them is to actually click on the image name in that, and I just closed that tab in my browser. So one way is to just click on the image name. Note that the image names have the exact time the image was taken right in the image file name. Moon, 2016, 09, September 5th at 1900 hours, 46 minutes and 35 seconds. And that's in universal time in England. So here it's either 4 or 5, and I can't remember with daylight savings time where we are at the moment, hours behind that. Okay, so that's one way to open it. The other way is to go to those robotic tools and click on JS9. And now when it opens, there's no image loaded. So we know that you guys might want to try this right after this webinar. And so under my list are all the images that were in my green archive. And you can see they're arranged by date. These are from last night. And these are from earlier, 8/29. But you're going to have nothing in your list until they come back tomorrow. So we also have, anyone who has an account has a list of archived images that we have. And so I'm going to open one of the archived images. Now we'll open the moon from back in January 2016 here. There's a moon. And I'll also open an Orion Nebula. So I want to note that the way the software works, here's an Orion Nebula taken through a red filter from what date? Anyone? You can see from August 29th. All right, so now under my list, if I go to the top, you'll see I have 2 images opened, the moon and Orion Nebula. The one marked in green is the one that's active. So this is telling you that kind of behind that, also open, I have a moon image. If I click on that, it'll take me to the moon. So you can have several images open in this image processing software at once. So let's stick with the moon. And I want you to notice a few things as I move my cursor around the image. You'll see some numbers changing. You'll see this number, pixel value, changing, and these numbers, physical location, changing. So if anyone wants to type in the chat box what they think those might represent, that pixel value and physical location. I'm moving here, I'll try to get way down here and move left. Now I'm going to move up. I see no one's typing, but okay. So we have a suggestion, pixel value is color. yeah, so I'm kind of moving my cursor all around the dark night sky, and you see it doesn't change much. It's 289. So, but what if I go to this bright spot? Right. So the, right. So that's exactly right. The location is the XY value, and here is X and Y of 0 and 0, and up here, remember I said it was 650 by 500 pixels. It's up in this corner. And the pixel value is a brightness value. And if you remember when you open an image, it automatically opens to tell you the brightest pixel value in the image and the dimmest pixel value in the image. Or actually, I'm not sure that's true because I'm only seeing 280s. I'm not sure about that low brightness value. That might just be set. So to find that 583, it's, you know, right here. Okay. So if I can set this high brightness limit, and if I set it at 4095, which remember I said there were that many brightness values that the telescope could take, that any pixel could show. If I set it that high, you don't see anything, even though if I get in here where I know the moon is, I'm getting pixel values in the 300s, which is above over here, or pixel values in the 200s. So anytime you get an image, it may not look like much, but if you bring this high brightness value down, watch what happens. Right? So this tool is telling the computer any pixel that's brighter than 573, color it white. Any pixel that's lower, in this case, than 409, color it black. And any pixel value that's between 409 and 573, assign it some value of gray, and the computer has 256 shades of gray available to it. So you can see that just from the scale down here, you can tell that this bright spot here, since it's white, must be in the 500s. And this bright spot here must be in the 500s. So the data of the image is not changing, but you're changing how you're displaying it and enhancing it. And if I lower this high brightness value, lower the low brightness, I get less black in the image. So there is a guide for using this that kind of goes over what I'm talking about quickly, and somewhere I have that here. Let's see if we go back. Yeah. So in your Educator Portal, you have curriculum resources, and they include an introduction to requesting images, which we just did, an introduction to image processing and image contrast, which kind of helps you understand the pixel value and some of the aspects of JS9. So I just want to mention that there's printed materials related to what I'm talking to you in the portal as well, and there are video tutorials about how to adjust the images. So we can adjust the brightness. If I open up my Orion Nebula image, again, when you first open that up, it looks like there's not much there. And you notice that the brightest value in this image is 4095. And in fact, it's these stars here. And you see there's something a little weird about these stars in the image. Let's bring this high brightness value down. And you'll start to see more, right? So now I'm making dimmer and dimmer pixel values appear white, right? As I bring that down. So, the first thing you want to do when you open an image is play around with these controls. The controls over on the right allow some finer tuning. And let me, in order to show what those do, I actually want to show you the color feature. So this is the most fun for students and adults, is the fact that you can assign all these different levels of pixel values shades of gray, but you can also assign them shades of watermelon or shades of fire sky or shades of candy. I'll note that Frank's children gave the names to these color palettes. They had this image processing tool is actually used by the professional astronomers here at the observatory, and we've adapted it to make a little bit of an easier interface for students and educators to use. And one of those easier interfaces is making the color names a little more evocative. I'm going to choose Rainbow 0, which is a color palette that rather than 256 shades of color, actually only allows 9 here. And I'm choosing that because I want to show you the, actually, somehow I'm not, why am I? There we go. So this stretch and shift, this contrast tool, you can see I'm stretching the color values out over more values or squeezing them over fewer values. Stretch and squeeze, stretch and squeeze. And that tool allows you really fine control over which part of the image you're highlighting and you see the most detail. This shift tool, if I click, I'm going to click multiple times on the left side. So shift down, shift up. So again, that tool, basically an image processing software, is just a paint by number tool. It's a computerized paint by number tool. And these controls allow you to have a lot of fine tools for identifying the, for getting as much detail out of an image as possible. Because of course, remember, this image of the Orion Nebula, if I put my, I'll go back to Fire Sky here, and we'll kind of do this, and I don't know. All right, there we go. So I'm seeing all this stuff out here, and if I put my cursor in there, I see that this nebula, the brightness value is 357, or 360. And out here where there's no nebula at all, it's 296. And we have, remember that in the middle here, where it's really bright and where those stars were, you're getting in the 2000s. So the software allows you to see things that are barely brighter than the background. And that's something that astronomers need to do with dim objects. All right, so again, your mission is to explore the various tools of the image processing. I'm going to show you a few more. Let's see. I just want to check here. All right. So once you've played around with an image and you like it, I want to show you a few other tools that you should know about before post for this week. One is a pixel table. And this allows you to really see, if I go up near this star, you can see that the star itself is 4,000, if I got there, is 4,060. Yeah, the center of the star is saturated. It's as bright as our detectors can go, 4,095. All the little pixels around it are in the 4,000, 3,000. But out here in the night sky, everything's in around 305. Okay. In here in the middle of the nebula, we're getting much higher brightness values, with some areas completely saturated. Okay. So the pixel table is a nice tool. A magnifier allows you to look more closely, and now you can see the individual pixels in the image. And in fact, you can also see that by zooming into the image. If I keep zooming, zoom 2, zoom 4, well, now I've got it off the center of the screen, so I want to use my panner to pan, right? And now if I zoom even further, zoom 8, now I can really see that this image is made up of individual pixels that were the pixels in the original digital detector inside the telescope, each of which recorded a value based on how many photons of light hit that part of the detector. All right. We'll use some of the other tools at a later time, but let's zoom back out. And let's say I kind of like this. I decide I want to save it. I can create a regions annotating parts of it. And I might put a circle around this. And I might put a box. I want to highlight this star that seems actually saturated. It's drippy, right? And then I'm using a text region. And if you double click on the text region, I can add a label. Orion Nebula. And I'll hit apply. And now you see my text thing says Orion Nebula. And I can make that larger just by grabbing the corner of it. And I can even give it a jaunty angle. All right, now I decide I like this, so I want to save it. When you save an image that you've processed, you want to save it as a PNG file. Saving this image as a FITS is basically what you want to do when you want to download it. The FITS image is the astronomical image format. It's the professional format, and it's what the JS9 is working with. And it's important for astronomers because it has a lot of metadata associated with it. But when you save an image that you've already processed, you really want to save it as a PNG. So I'll hit save. My computer is going to ask me where to save it. Yours might just save it in your download file, but you should be careful if your computer does that, makes that choice, because the automatic name of an image, if you don't change it, is js9.png. And so one important file organization note is that whenever you save an image, you probably want to actually label it rather than have all your images called js9.png. So I'm going to call this Mary's Orion Nebula Neb 09 06 2016. Okay. So now I have that. If I open it up, you can see I have the image saved. And now that you have it saved, you can upload it back onto the forum. And that's the last thing we're going to do in this webinar, because that's your homework for this week, is to open up some images, process them the way you want, experiment with the image processing tool, save an image, and then post it into a discussion forum to share with us. And I'm going to show you how to do that right now. So we'll go back to the main page. And we're going to post it to a discussion forum in the Educator Portal. So I'm going to go back up at the top. You always have breadcrumbs to navigate by. I need to go back to the main YouthAstroNet, go into the Educator Portal. Somebody else has introduced themselves. Thank you. Here is the request and process an image discussion forum. So I'm going to post my Orion Nebula that I just downloaded as a PNG file into this forum. Okay. And so I'm going to add a new discussion topic. And you'll see back in May, a lot of people replied with 18 images. I'm going to add a new discussion topic that says September cohort, post your first images here. Okay. So here is my first image from the webinar at 3:30 on September 7th. I realize I just said 6, didn't I, in my image? Okay. So I've typed a little bit. Now, the interface for posting discussion topics, if you click on this button here, the toolbar toggle, you actually have a lot of text editing features. So you can change the fonts and the sizes of what you type and things like that. But to enter an image, I'm going to hit return. I click on this little mountain photo. So I click on that. You get a general text box to upload an image. I'm going to click upload. It asks you, where do you want to find that image? And I want to choose it from my desktop. And I remember I put it in download, so I'm going to click on that image. Okay. And if you don't say save as, it'll just save as the name you gave it, but you might want to rename it if you suddenly find you're uploading a js9.js9 image.png. Upload this file. Okay. This appears to be the one I intended to upload. Good practice is to add an image description because you're adding it to a web page, and so this is the alternative text for screen readers. So I'm just going to call this Orion Nebula. And then I can insert it. And there it is in my text editor. Now, this is pretty big. If I wanted to not have my post be so large on the page, I can change the size of the image. If I just highlight it and shrink it a little bit, I can make it a little smaller. So there it is. So you note that I added the image by hitting the little mountain, not by using this attach feature. You want to not use the attach feature because it doesn't actually, people won't be able to see it when they look at your post. They'll have to actually download it onto their computer. All right, so I'm going to post to the forum. And there's my post, September cohort. Post your first images here. There's my post. And your mission for the week is to reply to this post with an image that you've taken, processed, colorized, downloaded, and do that by next week. And next week we'll learn some advanced image processing, including creating true color images as opposed to false color images using the 3 color filters that we saw were available for the Andromeda galaxy. So I'm going to stop now and ask if there's any questions. Any tips for saving these images on Chromebooks? I think on a Chromebook you can save temporarily an image file and then upload it, right? Because I think we've done that. When you hit save as PNG, I think it saves temporarily on a Chromebook. I wish I had Frank here because I feel like we just did this. And of course, if you have a Google Drive, you can save it to there, associated with the Google Chromebook. Let's see.
What he said he'd do.
Ah, there we go. Okay. There they are. Great. Other questions? Okay. All right. So we've learned how to take an image, and remember you're controlling the shutter for exposure time. You're controlling this filter wheel. This is kind of what it looks like inside the telescope. These are the telescopes in Arizona during monsoon season when it's much greener than in the last picture you saw. Luckily, we're through monsoon season mostly, so it's usually clear in Arizona. If it's cloudy, you're going to get images that look like these or like the first one that I opened. We've gone through that. We've experimented with that. And again, here's a little quiz to see if you understood the pixel value. So imagine this is a detector in a telescope that only registers 8 values rather than 4,096. And you'll see that there's a couple of pixels here that are a lot of light fell on. Pixels around that pixel values of 6. Here's pixels where a lot of light fell. So if we use the image processor and we color values of 8 as white, values of 1 as black, and values of 6 and 4 as shades of gray, can anyone make a prediction as to what this is an image of? I'm looking for a prediction of what this might be an image of. If 8 is pixel values, we're going to assign white. 1, we're going to assign black. 6.
You got some guesses.
Yeah, okay. Let's check it out. Yes, right. So essentially, these slides are available, by the way. They'll both be linked in the portal. Actually, that's probably the best way at this point to just get them. They'll be linked right within the portal under the Educator Portal. Okay. So the skills kids are using are the same skills used by professionals. One of our science mentors actually uses JS9 every day because he processes images from the NASA Chandra Observatory into press release images. I'm going to quickly run through the kinds of projects that can be done with the telescopes, just to start you thinking about the kinds of projects you might do. Kids can take images of the moon every day, create their own moon calendar, just as Galileo did. Find out, they can even measure shadows, measure craters using that image processing tool, and I didn't get to any of those features. So in addition to just colorizing, you can use the image processor to make measurements and of both brightness and scale. As someone asked earlier, you can take several images of the moons of Jupiter and create an animation. The image processor allows you to animate a number of images in a row. You can also take asteroids and see the asteroid moving. You can observe sunspots over time, observe the sun. Now, I will say the sun is the one object that you might frequently get a failed image because it's the one object for which there is a human in the loop. We have to put manually put an extra filter over the telescope to protect the detector from the sun. Frank does that, but of course he can only do it on days when it's actually sunny in Cambridge and days when he's here. So if you ask for an image of the sun on a Friday or on a Saturday, he might not be here and you'll get a failed image. If you ask it on a day it's cloudy in Cambridge, you won't get one, but keep asking and you'll get images of the sun. And a key thing about MicroObservatory images is that if you take them all with the same main camera at the 1 degree field of view, all the images, unlike textbook images, are at the same scale. So it gives you a much better sense of size and scale. For example, in the image on the right, both the moon and another planet, solar system planet, are in that image. A planet that's much bigger than the moon. And if you look closely, you might be able to see Saturn, which is much farther away than the moon. So in the MicroObservatory, it appears much smaller. Okay, I think what I want to go to right now is your next steps. You want to get on the portal, introduce yourself in that discussion forum, request an image or 8 or 10 from the telescopes, process the images with the JS9 tool, and post in the request and process an image forum. So you can post questions all throughout. The whole team here will be monitoring the forums and answering questions during the week. And we actually didn't show you how to create a wiki page. We'll do that in the next webinar. But if you want to play around with that, there is a share your images wiki that you can use as well. All right.